Yeah, boy. Number 9.
Yeah.
Lecture video 9.
Lewis models of atoms.
I'm glad we stopped introducing ourselves. You should know who we are by now.
Because I'm Monaco.
At Milks.
We just did it again. We're trying to take those boring models we did last lecture and make them a little simpler.
Yeah, let's do the Lewis dot diagrams. And these are actually the most relative ones as far as usefulness.
Yeah.
Because we don't really need to know necessarily how many neutrons there are or how many kernel electrons there are because they don't be doing nothing.
Love the use of the vocabulary. And one of my favorite subatomic particles.
Oh, nice.
There's only 3.
Yeah. Same learning target, except for this one we're going to focus on.
Same, but different.
Because Bohr and Lewis, here we go with the Lewis.
Yeah.
Okay, so all we need to do with Lewis dots is represent the element, symbol, and the number of valence electrons.
So those super common letters everybody knows is going to take the place of both protons, neutrons, and kernel electrons.
Correct.
In our models.
There you go.
There's a specific pattern for how we write the electrons around the kernel and the nucleus.
Yes, and this is it.
That's it.
We're going to write the symbol. We're going to draw a dot for each valence electrons on the north side next to each other, the east, south, and west side of the symbol.
Mm-hmm.
And there's rules for adding these dots. And the rules state,
Sure.
the first 2 go together and then 1 at a time around a bus. Can't have more than 2 on either north, south, east, or west.
I think that's a Pauli exclusion principle in practice.
Oh, is it? It kind of is. And yeah, that's the up
There's
and
the
down spin.
alpha.
Yeah, Pauli exclusion is up and down spin, opposite spin. And that is why they fill the way.
Alpha principle?
Well, it's been a long time for us.
I'm not sure anymore.
It's been a long time for us. But let us, drawing this Lewis dot of ions,
Mm-hmm.
ions have gained or lost an electron, specifically in the valence shell.
Who's got this one? You know, or Monaco? I'll take it. Symbol stays the same.
I was going to say rock, paper, scissors. Let's see.
The number of electron changes and a charge number is placed in the upper right corner to represent the number of electrons lost or gained.
Yes, so we do have to include the charge or it to be wrong.
Mm-hmm.
Good job.
For each unpaired electron, each dot is going to be can form 1 bond.
Yeah, so if it doesn't have a partner, it's looking for one. That would be the bond.
Exactly.
Okay. And we're going to do this now. So I'm stepping to the board. And somebody's talking me through with one of those big bad periodic tables.
Like these.
We started with the hydrogen. Hydrogen symbol is an H. Very
Yep.
good. And how many valence electrons does hydrogen have?
Just 1.
So I can only draw 1 dot. And every unpaired electron, which is lone, can form a bond. So hydrogen can form 1 bond.
Yes.
Excellent. Onto
Yes.
helium.
Helium.
Symbol.
Symbol for that is capital H, little e.
Pretty good.
We've got 2 valence electrons.
So I go like this, and I rule is first 2 together, then 1 at a time around the bus. Not this element, next element. How many unpaired electrons do I have?
None. They're both,
0.
all of them
They are
together.
paired. So helium will form a 0 bonds, very unreactive.
That is correct.
We've got lithium. That's Li.
Capital L, little I, got you.
There are one
One valence electron, but its electron configuration is 2-1, but
Yes.
valence is that last number. So it's going to be, and look, its valence electron configuration looks just like hydrogen. Very good. And how many unpaired electrons?
1.
So I will form a 1 bond. Pretty good.
Beryllium.
Ooh, I think I know it is beryllium Be.
Yeah.
Very good.
It's good.
Can I get the whole electron configuration, please?
2, 2.
2, 2.
2-2.
I can't be wrong no matter which 2 I pick, but it's gonna pick that 2. And the rule is first 2 go together. Then 1 at a time around the bus, but I ran out. Okay. And so I form.
They're all paired, so no bonds.
Very good.
Boron's a B.
Boron just a B.
The electron configuration, the whole thing is 2-3.
Gendoke.
So the first 2 are going to go together.
Oh, I need to do 3, not
Right.
the 2. Rule is first 2 together.
And then the other one can go on that east side.
There we go. And how many unpaired electrons?
1.
Excellent. So I form a 1 bond. Somewhere on this chart is something a little bit more complicated. Can you pick me one with more valence electrons, Mr. Monaco?
Carbon.
Not carbon. Carbon
You
breaks
wanted
the,
complex, bruh.
carbon breaks the rules. I want a filling order complex. So some 6, 7, 8.
Fluorine.
Fluorine is an F.
2-7.
2-7. So I need 7 valence electrons.
Bingo.
Rule says first 2 together, then 1 at a time around the bus. And this is what we mean by that.
3,
3,
4,
4,
5,
6,
7. And it would form one chemical bond because it has one unpaired electron.
There we go. And what he's talking about is this one right there is not paired. So I just wanted to give you one where we actually had to go around the bus.
Yeah.
Good.
Sounds great. Are we done?
Ooh, I think, well, you aren't done. You have a bunch more of these to do.
Correct. Bye.